Give you a recap. Last the first part we actually do logarithm increment, if you remember, and then we start to give definitions and deriving the equations. Okay, so now we actually have to derive a meaning for to predict a resonance, whether is it big or not, and stuff like that, if you remember. And then we use the typical solving method. We understand the movement, we draw our FBD, and you set up the equation, you simplify, and then now we have to find ways to further simplify the equations. So previously we actually do these things, okay, and then eventually we retain this equation, and we say that we will actually use this equation to solve. So if you still remember, this one is actually the second order non-homogeneous equation, and this solving method is the same as last time when we do the column friction, if you remember, the sliding thing. We also have a second order differential equation, right? It's the same thing. There is a force, the friction force, you remember. So apparently when you want to solve this thing, you need to have a complementary function and a particular integral, if you know, if you are solving a non-homogeneous second order differential equation. So therefore, using the same thing, we actually have to we actually solve for our whatever thing that we want. Okay, so now there's an important concept over here. The key difference why there are so many equations out there, okay, for second order, is because you plug in different complementary function and you plug in different particular integral. This is why this is why when we reaches this stage, okay, when we reach this stage, find ways to simplify the equation and get answers. This stage is the most random stage where a lot of we use what we have seen and what we have measured to actually sub into our equation to derive our answer. So in this case, they actually use the sine plus cosine thing. So but this one is the column function, okay, this is the column. So however, for our complementary function, we actually choose the underdam equation, if you remember. Okay, so how does this underdam equation come from? If they say you're gonna derive a complementary function for this thing. So if you were to remember, okay, so hold on a while. If you remember last lesson, we talked about free vibrations with viscous friction, or in other words, free damping. So this system, as you can see, is the same as what today we are doing. Okay, it's the same as what we are doing for. It's just that the amount that the force itself is different. Okay, the force itself is different. So that's why we can use this analogy. So last week what do we have see? So last week we actually derive the same thing using eventually we will derive a homogeneous equation, right? So this thing will be used for our complementary function. So this concept can be used into our complementary function, and therefore when you do all these things, okay, you solve, you use quadratic equation. Eventually you'll get the general solution for this, and then when you sub in your damping factor, you eventually get, if your damping factor is less than 1, you'll get underdamped. So this is why we have this thing over here. So if you forget, you can actually head back to the previous lesson and go and check it out. So this is just a brief talk about that. And then now what is the particular integral? Okay, if you were to remember, particular integral is remember the typical particular integral. If you have a constant, you sub in a lambda. If it's a constant times x, okay, a variable, you have, you know, these things. And if it's kx squared, then you have to do out this equation. Okay, so if you remember last time the second order differential, the particular integral, if you remember the method. So if it's cosine, then you need to, the particular side, you have to have cosine and sine, and then you differentiate 2 times and then you sub in back. So you remember? If you don't remember, then it's okay. Just to let you know. So nonetheless, however, this in our situation, we are not using one of that particular integral, one of that form. Okay, so we are not using any of this form. Okay, as you can see, our form is what is it? Our form is actually x cosine wt minus alpha. I mean, yeah, some things. So so this is different from the typical particular integral, and this is a very important understanding. Okay, and up till the previous lesson, okay, last lesson, deriving this is pretty easy. Okay, it's pretty straightforward. You follow the similar trend, but once you come into this zone, what to sub in as your complementary function and your particular integral, you have to really be careful. So this portion is very vital. Okay, so please remember this portion here. What to sub in for complementary function and your particular integral is very vital. You sub in wrong, you are dead. Okay, so with this, I hope that I can let you understand how we derive um, up to here and the meaning and the importance of this thing. So let's start off with today's objective. I talk so much. Okay, so previously we actually derived this equation. Okay, from this is the last part of over here. Okay, and let us call this equation 1. And to solve for x, okay, to solve for this x as you know is the distance x from a datum point. Okay, so hold on again. Yeah, so datum point over here. So this is the distance x moved. Okay, it's different from the position. This point is the position x. Okay, so this x equals to complementary function. So in order to solve this x, because our variable is this, right? So therefore, to solve this, we use complementary function. This is under them. I've explained. So particular integral wise, we use this one. This one is the forcing function. Okay, if you remember, the forcing function is if it's f naught cosine omega t. The reason why it is in terms of the position x, okay, is that hold on. So this is the meaning of why the amplitude itself x, okay, is somewhat proportional to force. Okay, so I have drawn this diagram, and as you know, this is a simple free vibration one, but I use this as an example. So you pull this force with a certain force, right? And up to this portion over here, it is equals. So when you release, the force is equals to the reaction force minus kx in the in that in the opposite directions. Okay, minus kx. So let's say this is x naught. Okay, this is the equilibrium point where you didn't before you pull it down, it is static. Okay, this is static. So in this case, in a graphical view, this is this point is x naught. Okay, and then this point is x2, and this point is x1. Okay, make sure this is the position x. I'm talking about the position. Okay, so as you put it down, okay, and you release the minus kx, the kx start to, okay, hold on a while again. So when you release, the amount of the x distance is gonna be large. Lesser and lesser. Okay, eventually go to x naught, right? So the amount of distance will be somewhat lesser and lesser and lesser. So still, because this x naught is the so-called the 0 point, and then this below x naught is actually the negative area. So in this case, it's negative x. Okay, I mean not this area, I mean around here. So what I mean is, along this area is minus x, right? So as the minus x decreases, the amount of x1 distance, okay, x1 distance is here. So the amount of x1 distance decreases, right? Okay, so this is what it means. And then if the okay, hold on, it's very hard to explain. In other words, the position x1, okay, is over here. So this one, this diagram is an opposite of this diagram. Okay, you're plotting against amplitude. Okay, from the x naught. So nonetheless, so this one is positive or this one is negative. You would say negative x2. So it's a little different. So the x itself is this value over here, minus x, right? So when you put it down, you have a minus x distance, and you release the minus x distance is gonna be slowly decreasing. And so when it reaches here, it's and then x, and then up to here, this one is positive x already, right? This positive x. So this one will become negative. This is why I say that this portion here is this whole thing is opposite of this thing. So whatever plus over here is minus over here. Whatever minus over here is plus over here. So this is plus, this is minus, and this is minus, this is plus. Okay, so this is why there's opposite relationship. Okay, I may be wrong, okay, but it sounds right. So I just don't want to waste time, so let's continue first. So as I say, if the x if the x is getting, the distance over here is getting smaller and smaller, the position will start to get going near to the position of the datum, right? Eventually it will reach x2, and you'll bounce back here and then comes down again. So this relationship, so minus kx, in other words, is the is taking x naught minus x1. Okay, so how do I say it? So minus kx is actually x1. Okay, so in other words, x1 is equals to minus kx. The amplitude of x1 is equals to minus kx, while the amplitude of this portion over here, this portion over here, is equals to kx. Okay, since that's the convention itself. So the amount of energy within this thing, okay, the forces, the amount of forces can be illustrated in terms of the position of where you last stopped. Okay, because since this one is minus kx, right? So if you were to, when you sub in minus kx, minus x1, okay, minus x1. So maybe I should hold on again. This should be clearer. Okay, minus x1 is equals to minus kx. So if x naught minus, if x naught here, x naught over here minus kx, it will be x naught plus kx. Okay, so eventually you will reach x1 over here, right? Hope I make sense over here. So and for another example, so if x2, okay, the position x2 over here, right, it's plus kx. So if x naught minus x2, or in other words x naught minus kx, you have the position at x2 itself. So it's a little, my math may be wrong over here, the equations may be wrong, but I hope the concept is being conveyed in a well manner. Okay, so in this case you can see that the forces and the position are somewhat related. Okay, they are somewhat proportional. Okay, so they are somewhat proportional, and this is why so I've talked so much about it. It's just saying that the forces itself can be replaced by the position x, where x can be this x, can be this x. So it can be any point of the because this whole y-axis is the amplitude, right? This whole y-axis is the amplitude. Okay, so it can be this x over here, it can be this x over here, it can be this x over here. So this whatever x is in terms of how the cosine graph would grow eventually. So the cosine graph is in terms of the frequency itself, natural or damping frequency, and then maybe there are some phases. Okay, for this portion I totally have no idea what is it, but nonetheless, I believe I believe I had explained a very well understanding to you. at least, okay. So in the future, if you find something wrong, then you can just edit. But nonetheless, I have this set. So I've talked too much, and then I'll just summarize why I've talked so much. Okay. So we have this equation from last video, and then to solve for x, we say that we need to have complementary function and particular integral. And complementary function, we know that it is under them. So we also talk about particular integral, where we how we choose particular integral. We actually use this thing. I mean, just now the analogy. Okay. So next video I'll just talk about this thing. Okay. So why would we actually use the forcing function as our particular integral in this case? Okay. So let me repeat again. The particular integral is related to our forcing function. So what is forcing function? Is this one. So particular integral is related to this thing over here. So we're trying to explain to you. So next video will explain to you why we do that, and then why you use the forcing function as our particular integral, and then we'll explain the rest, and we'll set up for a new, and then we'll continue using vector polygon. So see you.